This episode is brought to you by Brilliant. Probably two of the most common and important questions in astronomy are what black holes are and what dark matter is, but many wonder if dark matter and black holes are the same thing. Others suggest black holes might be the key to finally shedding some light on dark matter. What are black holes? What is dark matter? And do they have anything to do with each other? The simple answer is yes, they are very related, we're just not sure how much. And today we're going to talk about both the notion that mysterious dark matter might be composed of black holes, and the newer idea that we might be able to use black holes to learn more about dark matter. One thing both have in common is they are seemingly invisible except by their gravitational effect on the outside universe. And that's probably a good place to begin for the entire subject, because until the last couple of decades, there was real doubt about if black holes actually existed, and many folks still wonder if dark matter itself is just some measuring error. Both concepts are similar in age to the term galaxy coming to mean one of many giant clusters of stars dating to the early 20th century, and are very much intrinsically connected to that early understanding of our universe being vastly bigger and distinct from our galaxy. We had some suspicions about black holes as a possibility even before Einstein predicted them as a consequence of general relativity, and at the time, the theory of choice was still a steady-state universe that was assumed to be infinite in size and age, and the notion that stars ran on fusion, rather than just being hot from gravitational contraction, was just popping up too. At the time, we thought stars started hot and cooled with time, and it turned out to be the other way around. Either way, it was assumed that stars cooled down, died and went dark, and that the universe might be littered with all those remnants. We were starting to be able to calculate the mass of our galaxy once we understood the concept of galaxies, and we were guessing at the number of stars and seeing that, based on their mass, there just weren't enough of them to cause the orbital rates of stars around the galactic central bulge. More mass means faster orbits. There was a lot of missing mass, but it was generally assumed that this was dimmer stars, gas giants, nebulae, interstellar gas, dead stars, and so on. And a lot of it was, but the problem was, as we got better and better at astronomy, we were able to survey many of these types of objects, and we just kept coming up way short. For decades, we could kind of handwave that because there were so many question marks and huge margins of error on those estimates too. Estimating the density of interstellar dust, for instance, requires knowing the distance to some stars so you can see how much light is being absorbed by gas and dust for every light-year distance between you and them. But not only does that amount change significantly between various regions of the galaxy, but we often had star distances that, at best guesses, were off by 50% or more. It is also very hard to count dim objects, and virtually all dead stars qualify as dim compared to main sequence ones, let alone red giants or hypergiants, which are not that common but seemed a lot more common in early days of astronomy, since we could see them much easier than regular stars, let alone stellar remnants. Indeed, we had problems seeing even stars like our own sun beyond a few thousand light years, even with big early telescopes. So a lot of the stars we saw early on were giant stars, hundreds or thousands of times brighter than our own, resulting in us mislabeling our own sun as a yellow dwarf, even though 19 out of every 20 stars is smaller than our sun, and that's not even including brown dwarfs. Most stars turned out to be red dwarf stars, and one just a tenth our sun's mass might only be a thousandth as bright. So essentially, we knew about that weird paradox in galactic mass for a long time, but since we had so many uncertainties in this mundane matter, looking for an entirely new type of matter that was also basically invisible was not easy, and we weren't sure it was necessary yet. Also, a lot of folks figured all this missing mass would just turn out to be black holes, old and cold white dwarfs and neutron stars, and a lot of Jupiter-like and brown dwarf objects. We had assumed there was really only two events that could form black holes at this point, a supernova and the immediate moments after the Big Bang, what we call primordial black holes. Supernovae are so bright they briefly outshine a galaxy and come from stars that are thousands of times brighter than our own, so we had a fairly decent guess at how often such black holes were formed fairly early into our observations. It might have been a few times larger or smaller than some estimates, but it wasn't making a dent in that missing mass. Even that monster black hole in our galactic core, probably massing 4 million solar masses, is peanuts compared to galaxies massing several 100,000 times as much. For post-supernovae black holes, even permitting many to gobble other stars, which would be a very bright event, we couldn't plausibly give them even 1% of that missing mass without them gorging on other matter so fast we would easily notice. However, we had no idea how many primordial black holes there might be, and even given the insane conditions in the moment right after the Big Bang, where even the interior of a giant star would seem cold and mild in comparison, it wasn't too crazy to think that maybe most of the mass of the universe got itself squeezed into a lot of smaller, primordial black holes. Indeed, one the mass of a freight truck, say 10,000 kilograms, would be millions of times smaller than an atomic nucleus, and if you got hit by one, rather than plowing you down like being hit by a freight truck, or sucking you into itself like the typical black hole in sci-fi, you would never know it even happened. It's statistically unlikely it would hit even one single atom in your body, any more than a baseball-sized rock is likely to hit the sun if it were randomly tossed into our solar system, and even if it did, it would just suck in that one atom and keep on moving. You wouldn't be sucked into it any more than you get sucked into a freight truck by its mass. By the 1980s though, we had a lot more data, and one critical new theory about black holes is one that propelled a young physicist by the name of Stephen Hawking into fame among physicists. He took quite an interest in primordial black holes as an option and studied the concept. He'd proposed that, if black holes exist, which was still debated at the time, then we should see the occasional dribble of thermal radiation off of one, what we now call Hawking radiation, and which we've discussed in more detail in our black hole series. The amount was pitifully tiny in the case of supernovae remnants, but as they slowly radiated energy and lost mass, the rate of energy loss would increase. Indeed, it meant that the freight truck mass black hole I mentioned earlier would be radiating fully 1% as bright as our entire sun, though thankfully it would be radiating so much mass energy to do that, it would only last a few millionths of a second. This of course has interesting possibilities for starship drives and weapons, see our black hole series for more discussion of those. But what this meant was that you could predict the lifetime of a black hole from its mass, and one that was formed massing 210 billion kilograms or 210 megatons would have been getting brighter and brighter until expiring today, 13.8 billion years after it formed, assuming it hadn't snacked on anything in the meantime. Any primordial black holes more massive than 210 megatons should still be around and nearly invisible. That sounds great as a dark matter candidate, but we don't have anything telling us that only black holes more massive than that could have formed. Practically speaking, any primordial black hole massing less than 6 megatons would have expired before the surface of last scattering, the point 380,000 years after the Big Bang, where the universe had cooled and thinned enough to let neutral hydrogen form, and that allowed photons to travel without almost instantly running into something else, and this is when the cosmic microwave background radiation is from. We would see no evidence of black holes formed during the Big Bang that died before this event. So, the search for primordial black holes between 6 and 210 megatons allows us to hunt for black holes that might have died since the surface of last scattering until modern times, and there's no background glow of radiation in the right ranges, with no other known source to account for this. This dealt a bit of a blow to the idea of primordial black holes being dark matter. However, primordial black holes have so much going for them as candidates that there was, and indeed still is, a great reluctance to knock them off the candidates list. They are definitely still in the top 10 and probably the upper half of that. There are good reasons not to knock them off that list yet, even if the weakly interacting massive particle, or WIMP, does seem a better option for dark matter than the MACHO, massive, compact, halo object. Now, machos are not limited to black holes, but massive and compact could include a brown dwarf or a black dwarf, or even some exotic options like cosmic strings, I suppose. The halo part of machos comes from us getting better at calculating mass locations from orbits of stars around the galaxy, and notice that the missing mass was spread out in a roughly spherical glob for our galaxy, which is more disc-shaped with its stars, and with other spiral galaxies too, as well as spherical galaxies. Most of that matter is dark, not giving off light, visible or other frequencies, and is in a spherical blob. Most in our galaxy is mostly in a disk form for the same reason solar systems tend to have their planets fall into a roughly disk layout. Stuff tends to whack into each other until you get an averaging effect of momentum and inertia in a loose disk, which slowly congeals into planets and such, or at the galactic scale, nebulae and stars. Massive but compact objects, though, can potentially avoid this simply by having so much inertia compared to their collisions that they are still very close to their original orbital paths, which by default would have been more random and thus spherical in layout as a whole. Also, we know the effective temperature, which is essentially speed, of these halo objects, big or small, because we know what the escape velocity of the galaxy is. There is gas and dust still in a spherical blob around the galaxy too, even if it is mostly in the disk, and we call this the Galactic Corona. It is moving very fast, but not quite fast enough to escape our galaxy's gravity. This gas and dust has an effective temperature around 1,000,000 Kelvin. It wouldn't burn you because it's so diffuse, but it's still hot. Or rather, cold. This is where we get the notion of cold dark matter from, because dark matter does appear to clump around galaxies, as their velocities or temperatures are not big enough to be permitting them to be evenly distributed around the universe, rather than clustering around galaxies that have sucked them into orbit. Now, 1,000,000 degrees might seem absurd to a virtue-ass cold, but everything is relative, and the Big Bang was incredibly hot. We know dark matter is old, as we can see it as far back as we can see anything, to that surface of last scattering, as before that all light got reabsorbed by matter. We assume it was formed during or shortly after the Big Bang, primordial. The only way for primordial dark matter to have lost any temperature or velocity is to hit other things, which would result in the more disk-like distribution we see of mundane matter in galaxies. That means it does not interact much, and when it does hit something, very little of its inertia is lost, which fits either an object that is exceedingly weak in its interactions or which is just insanely compact and massive, like a black hole, which is not much slowed down by running into the occasional atom. But this also means that dark matter isn't hot, or isn't moving at ultra-relativistic speeds like neutrinos do, so close to light speed as to make no difference. Neutrinos are common and have a little mass and interact with virtually nothing, passing through our planet as though it wasn't there, but they cannot clump around a galaxy and orbit it because they move hundreds of times faster than the escape velocity of galaxies. They would be an example of hot dark matter, and indeed, it isn't that they aren't dark matter themselves, it's that once we detected them and were able to get a mass range for them, less than 1% of the missing mass, we excluded them from dark matter, same as we have with galactic dust, gas, brown dwarfs, and so on, because dark also means unknown. Which is a good reminder that we don't know that the remaining dark matter is one single thing. It could be a range of options dividing up to form that mass, related or totally unrelated to each other. Anyway, there's reluctance to let black holes go as dark matter, and for good cause. Here are some of the reasons given. First, we have no experimental proof that black holes give off Hawking radiation. That's why Hawking could be the most famous and respected physicist alive in decades that still hasn't had a Nobel Prize. Those tend to go to experimentalists over theorists, because it has to be proven, and the only way to prove Hawking radiation would be with primordial black holes expiring. Post-stellar black holes are so massive that their Hawking radiation in its entirety is dimmer than any human eye could detect, even if you were close enough to be ripped apart by one, and the nearest known black hole is many hundreds of light years from us, and its Hawking radiation wouldn't power even the dimmest light bulb. Second, we do not know that it would function exactly as theorized. This is more important because to most of us in physics, the basic reasoning for Hawking radiation is so sound that we can't really see how it could be wrong, but some tiny little unexpected interaction or aspect utterly alters how something functions in practice. Third, we know nothing about quantum gravity yet, that strange realm of physics of how gravity operates down at the atomic scale. and every primordial black hole we might hope to detect Hawking radiation from is far tinier than any known particle. As an example, right now, no black hole that used to be the interior of a star is losing any mass, because while they trickle out a tiny amount of Hawking radiation, in theory at least, they also absorb a bit of gas and dust in excess of that anywhere they would be, even in intergalactic space. What's more, they would be absorbing that cosmic microwave background radiation, which would all by itself exceed what they lose to Hawking radiation, and which was also far denser and stronger in earlier periods of the universe, feeding them even more than now. Stellar mass black holes will only begin to evaporate away when the universe is so old and thinned out that the universe isn't adding mass or energy faster than the black holes will evaporate, trillions of years from now, when the universe is colder than their event horizon. Primordial black holes should be an exception to this, being so small they cannot even absorb an atom if they hit it, like a human mouth trying to take a bite out of a steel sphere the size of Earth, and which has to swallow the whole thing. We don't really know how black holes that tiny interact with things, or if they can even be made to exist. Cosmic microwave background radiation has a wavelength of about a millimeter, a trillion times wider than your typical atomic nucleus, and thus it doesn't get absorbed by them nor do atomic events emit them. They emit gamma radiation, much more energetic and shorter wavelength photons, very dense packets of energy. The assumption is that a black hole even smaller than that can't absorb one either, but there's a lot of ifs on that. If a subatomic-sized black hole can actually grab matter or energy better than we expect, then those 6 to 210 megaton primordial black holes might still be around. Even smaller ones might still be around too, since they could have been fed. Indeed, given that, during the period prior to the surface of last scattering, the universe was a much denser place, full of much shorter wavelength photons, each bearing far more energy. It is plausible that primordial black holes might have fed themselves up above a certain size, and thus all those too tiny to eat died before that period ended, leaving no footprints, and all the others got themselves up to a mass above 210 megatons, and thus are still around. Better Big Bang epoch modeling might let us accurately define that mass range for primordial black holes. Right now there's a lot of question marks. Amusingly, dark matter's nature being determined, be it black holes or not, might help us figure that out. We also don't know that the forces which could have formed micro black holes in that primordial epoch didn't favor discrete distributions. As best as we can tell, most subatomic and quantum things come in very specific masses. You don't get a proton that's twice as massive as the normal proton mass, or as best as we can tell, even 1% more massive. They seem to all be the same mass as each other for some reason. Same for electrons, muons, and so forth. They all have a distinct or discrete mass, unlike photon energy packets which can range from the 2 or 3 electron volts you and I can see to billions of times more, like gamma rays, or less, like ELF radio waves, and with no apparent cap on either side. Primordial black holes might have come in discrete sizes, one or many sweet spots of formation, and none in that Hawking evaporation range. Or they could have come in bands. We see distributions that are thick separated bands in nature fairly often too, like our asteroid belt, which is really multiple belts, thick bands and gaps. Now, how did those primordial black holes potentially form? Well, we generally accept that the early moments after the Big Bang didn't have nice flat or gently curved space-time. Think of a sheet of aluminum foil you crunched up into a wad, then tried to spread out, lots of crinkles and even some tears. Then imagine you used as a jello mold for a thin layer of jello. The resulting thin jello is going to have thicker and thinner spots and even total gaps, and that's essentially what we think that early universe looked like that caused normal and dark matter distribution and possibly even primordial black hole formation. Over the eons, this uneven distribution, plus dark energy, caused the clumping we see with galaxies and galaxy clusters and cosmic voids. There are a number of pros and cons to primordial black holes as a dark matter candidate, and I'm going to rattle through those fairly quickly. I just want to emphasize that, while they are not considered the leading candidate right now, they are still considered a strong contender. Here are some of the reasons why that's the case. Tiny black holes might not interact much with interstellar dust, but one passing through an incredibly dense object, like a white dwarf, could potentially reignite one and cause a runaway explosion or supernovae at rates which do not seem to occur in the universe. Supernovae are not common enough, based on how often we see white dwarfs and the necessary amount of primordial black holes to be dark matter. Black holes between 10 million and 100 million megatons cannot be a significant portion of dark matter. Stars between 100 million and 10 billion megatons are also doubted to fit. So too, the capture of black holes between 1 million and 1 quadrillion megatons by neutron stars, leading to detonation, would also be expected to happen often enough in dense old globular clusters that we would have expected to have detected it. Microlensing of stars as these primordial masses pass between us and other stars doesn't appear to happen as we would expect if they were in the mass range of 10 billion megatons up to low stellar mass. There is a lot of other good data in the last decade or so pushing against the idea that primordial black holes of stellar mass ranges are around too, and we just don't seem to be detecting many intermediate black holes, those of hundreds or thousands of solar masses that represent the range between the normal post-supernova black holes and big galactic core black holes. All of those leave plenty of room for debate. There is more too, but they get more technical in their reasoning. And we also have some ranges of mass that aren't accounted for as well. We think that primordial black holes, Planck relics, could also have been as small as a single Planck mass, about 10 micrograms, and again we would expect them at anything less than 200 or 300 megatons to have expired by now or be glowing hot with Hawking radiation. Does this mean that black holes are dark matter? Well, possibly. For my part, I favor WIMPs, and it doesn't bother me that this requires a particle more massive than a proton or neutron with very little interaction. Neutrinos barely interact, and of the 17 known elementary particles in the current standard model, of which neutrinos are 3, virtually every bit of mundane matter is made of 3 others: the up quark, the down quark, and the electron. 2 others, the photon and gluon, have varying mass or energy rather than specific discrete amounts. That's 8 particles, and of the remaining 9, only the strange quark and muon mass less than a whole proton. Half the remaining elementary particles mass thousands of times as much as the up and down quark, and hundreds of thousands of times as much for the electron masses. So another massive particle would not surprise me. And their mass has nothing to do with how they interact with things except by gravity, which dark matter also exerts. So a massive particle that just happened to be no more interactive than a neutrino is no weirder to me than a primordial black hole with some unexpected properties and discrete mass ranges. There's too many unknown unknowns in particle physics to even rule out something utterly mundane of source like tau particles and top and bottom quarks having some non-interacting particles they form, or even them and antimatter having, for unknown reasons, been common right after the Big Bang but biased towards falling into each other to make primordial black holes, which do not have to be made of baryonic matter either, like you and I and our planet and sun are made of. I would rather doubt it, but none of our contenders for dark matter, be it WIMPs or primordial black holes or machos or another, really deserve to rest confidently and easy as top contender. If you would like to find out more about those lesser-known dark matter contenders, we did an episode looking at them some years back in our Dark trilogy of episodes covering dark matter, dark energy, and dark flow in the Great Attractor that we did as a collaboration with my friend Joe Scott from Answers with Joe. Before we close out though, black holes represent a way we can learn more about dark matter, even if they turn out not to be dark matter themselves. Earlier this year, I was at a conference at the RAND Corporation that I'd been invited to by my friend Harold Scott, and one of their physicists on staff, Christian Johnson, was talking to myself and another attendee, David Kipping, about a paper he'd co-authored a few years back, Search for Gamma Ray Emission from Local Primordial Black Holes with the Fermi Large Ray Telescope, and another on electrically charged black hole relics, Direct Detection of Primordial Black Hole Relics as Dark Matter, which I'll link in the description. This was of course about the primordial black hole option, but the discussion led to the option of using the giant black hole in the center of our galaxy, Sagittarius A, as a dark matter accelerator that Christian looked at in another of his papers, And the reasoning goes as follows. Some types of particle-based dark matter options would have two particles of dark matter collide and annihilate, as with normal antimatter interactions, and this is called S-wave annihilation, and is assumed to release a specific amount of radiation dominated by the mass of those dark matter particles. The photons have their mass energy, plus some momentum energy from their collision, but not much, relatively speaking, so their energies are not really based on the speed of the particles for how likely it is to occur. And we look for that but haven't found it yet. Alternatively, in some models of dark matter, the speed of the particles would affect the energies in cross-section, and they think this should be magnified near a black hole where they're getting accelerated to very high speeds and densities and releasing radiation that would stick out from background noise, somewhere in the 10 to 600 GeV range, or gamma rays many billions of times more energetic than the photons we see with our eyes. In this case, there was no signature adding evidence against that range of dark matter, but it is a great example of how black holes can be used to help dark matter research and astronomy in general, and since that discussion inspired this episode, I want to make sure I gave Christian a shout out, and my thanks for some very pleasant and stimulating conversations. I think it also raises the point that we have learned a lot about both black holes and dark matter in the century or so since we got a hint of them, and while they're mysterious objects still, they may turn out to be the bedrocks of power and technology in centuries to come, something we explored more in that Black Hole series and our Dark Matter Technologies episode. They represent virtually unimaginable levels of energy and resources, and any civilization that learns how to manipulate or make them would be staggeringly powerful. Of course, they are mysterious, so it might turn out that learning to tap them is a dangerous process that could obliterate a civilization, and we'll explore that concept of technological time bombs in 2 weeks, and the possibility of wrecked civilizations fleeing such events next week in Alien Refugees. So we are well into summer, and while it's always nice to take a break from school, if you're a student or parent of students, it is important not to let what you just learned rust away over the summer. I like to think shows like SFIA with a math and science focus help keep that interest up, but it is still important to practice, and that's where our friends at Brilliant can help. Their online and interactive learning can help you stay in practice and have fun while you're at it, so you're not losing the knowledge you worked so hard to get. Indeed, they can help you learn even more and also help discover practical uses of math and science in your daily life. Brilliant's Everyday Math course provides a great new perspective on foundational math topics like percentages, fractions, and basic geometry. These topics are often thought to be hard to learn, but they do not have to be. They are much easier to learn with interactive examples. Everything is. The best learning is hands-on and interactive learning, hands down, and Brilliant is an amazing tool for learning STEM interactively. Brilliant makes it easier for anyone to learn, be it the basics or advanced materials, and is the perfect partner for a lifetime learner. With Brilliant, you can learn at your own pace, learn on the go, and learn something new. To get started for free, visit brilliant.org/IsaacArthur or click on the link in the description, and the first 200 people will get 20% off Brilliant's annual premium subscription. So we'll get to the schedule of upcoming episodes in just a moment, but if you enjoyed the music accompanying today's episode, those were all from Stellar Drone, who does some amazing and often haunting compositions. And like all of the music on this show, it is listed in our credit roll at the end of episodes and linked in the episode descriptions. Folks often ask in the comments who did this or that song so they can hear it more and more loudly, and as we mostly work with artists who kindly let us use their songs and are show fans, I like to make sure folks know where to find more of their great work. And speaking of more, this is our last episode for July, but we will have our live stream Q&A coming up this Sunday, July 31st at 4 p.m. Eastern Time, where you get your questions from the chat answered on any of our show's topics. Then we're into August to examine the notion of survivors fleeing disasters or attacks to new worlds like Earth in Alien Refugees. The week after that, we'll look at the possibility the reason we don't see any aliens is that they all blow themselves up with technological time bombs, leaving no survivors. Then it'll be time for our Sci-Fi Sunday episode, Dumbest Alien Invasions, where we'll examine the weirdest attempts and motives in fiction to invade Earth. If you want alerts when those and other episodes come out, don't forget to subscribe to the channel and hit the notifications bell. And if you enjoyed today's episode and would like to help support future episodes, please visit our website isaacarthur.net for ways to donate, or become a show patron over at Patreon. Those and other options, like our awesome social media forums for discussing futuristic concepts, can be found in the links in the description. Until next time, thanks for watching and have a great week.